Last week we transitioned from simple harmonic motion to waves. And we said there was two kinds of waves, two kinds of mechanical waves. There was the transverse wave that looked something like this, and then there was the longitudinal wave that looked something like this. There's a few things that I'm going to ask you to label right now on these two types of waves. Firstly, I want to label a crest. Where would I label a crest on one of these two waves, Ethan? Okay, this is the transverse wave, so the top wave? Okay, so the top of a transverse wave. Good. So that's one crest, that's another crest, and obviously that's another crest as well. What about the rarefaction? Okay, which wave am I going to label the rarefaction on? Transverse or longitudinal? And where am I going to label it? There, Kobe? Longitudinal wave, good. Sorry, an area of what? Good, an area of low pressure. So that's a rarefaction. That would be a rarefaction, and that would be a rarefaction. What about a compression? Where am I going to label that? On the transverse wave or the longitudinal wave? Good. And where am I going to label it on the longitudinal wave? Good. So where you have the dense or area of high pressure would be a compression. So these would be my compressions. Good. What about a trough? Which wave are we labeling the trough on, Andreas? Good, that's going to be the transverse, the top one, and where am I going to label that? Good. Good. Now let's label the wavelength of the top wave, of the transverse wave. Let's start the wavelength right here, and I'm going to draw a little line. I want you to stop, tell me to stop, yell stop, when I reach one complete cycle or the distance over which the wave repeats itself. In other words, the wavelength. Okay, tell me when to stop. You missed it. Yeah, that's the wavelength, the distance over which the wave repeats itself one time. We could also label it right here. That's the distance over which the wave repeats itself, or we could label it right here. Doesn't really matter as long as it's the distance over which the wave repeats itself one time. We wanted to label it down here. It's a little bit harder to see what a wavelength is down here, but it's not that bad. Okay, if I want to start right here, let's say, and the compression for a wavelength down here, where am I going to stop? At another compression, right? It's like labeling it from crest to crest or trough to trough, compression to compression, or we could label it rarefaction to rarefaction, the distance over which the wave repeats itself. What about the amplitude? Can't really label that on the bottom diagram. It's pretty tough, but on the top diagram I can. Ollie? Yeah, it's the highest point of the wave is measured from what? Or the other E word, the equilibrium? Yeah, so we're going to label the amplitude right here as measured from the equilibrium. It's the highest point, or we could label it right here as measured from the equilibrium, the lowest point of the wave. We ended the week last week talking about what happens when a wave goes from one medium to the other. It encounters a boundary between two different materials. Maybe it's between slinky and hand, as we did in the demonstration last week, or maybe it's between air and glass. Okay, whatever. There's a boundary between two different media or two different materials. We want to know what happens. Well, we know that in both cases, we know that whenever we encounter that boundary between two different materials, we know that there's always at least some of two different things that happen. There's always going to be some reflection and always going to be some transmission. Sometimes you get way more reflection than transmission. Sometimes you get way more transmission than reflection. Sometimes it's about 50-50. It depends upon the type of materials that you're dealing with. If the media are very similar, it's going to be mostly, Daniel, transmission. If the two materials are very different, it's going to be mostly reflection. There's always some of both, okay, but sometimes it's mostly reflection, sometimes it's mostly transmission. I want to focus on, right now, what happens to the reflected portion of the wave, keeping in mind that that's not the whole wave. There's always some transmission. But the part of it that's reflected can be reflected either right side up or upside down. If the wave encounters a boundary that it's attached to, then it's going to be reflected which way, right side up or upside down? It's attached. Think slinky with Ollie holding on to the slinky. Yep. Good. If somebody's holding on to, or it's attached by tape or whatever, if it's attached, then it's going to be reflected inverted. Now, sometimes it's a little bit difficult to think of attached or not attached because of the nature of the media. We're going from air to glass in the case of light. It goes from air to glass. Attached or not attached? Well, it's kind of hard to think of it that way, right? So what we do is think of less dense, more dense. When we're going from less dense to more dense, slinky to hand, then it's going to be reflected inverted. So think of it whichever way is more convenient given the nature of the media. Less dense to more dense, or it's attached. Then I want you to think that it's inverted, upside down. Yep, go ahead.
It's like UV, is that a wave?
Yeah, UV is a wave, yeah. Okay. All right. Now, if the wave, the medium that the wave is going through is not attached to the medium that it's going to, the second medium, then it's going to be reflected right side up, or right side up or upright. Sometimes it's difficult to think of it that way. So once again, we got to think of it in terms of density. So if we're going from more dense to less dense, we can say that it's going to be reflected right side up. So slinky to person, upside down. Slinky to air, it's going to be reflected upside down or inverted. Now, for the portion of the wave that's reflected, okay, we always get right side up or upside down, but we may also get an angular thing taking place here. It may bounce off at a certain angle. If it strikes the boundary at a certain angle other than 0 degrees as measured from the normal line, then we're going to find that the angle of incidence, we'll say this is 38 degrees, is always going to be equal to the angle of reflection. We'll say this is 38 degrees as well. Now, that doesn't mean that this stuff doesn't apply down here. It does. The reflected wave gets reflected at an angle, but it will be either right side up or upside down as well. We just can't demonstrate the slinky at an angle, so that's why you haven't seen that. Okay, this stuff still applies, just something else applies as well. Now, finally, the last thing that we dealt with last week, the other part of the wave is transmitted, which means that it keeps going. Now, maybe lots of the wave or only a tiny little bit of the wave, but when it's transmitted, we know that there's certain things that will change as a result of that transmission and certain things that will remain the same. I gave you an analogy on Thursday or Friday of last week. For those of you who are here, we talked about the parking lot, which is pavement. And then we talked about the swamp right next to the parking lot, which is 30 centimeters, let's say, of water. And you're trying to walk through this water, and you know it's harder to walk through the water than it is to walk on pavement. We've got soldiers, for whatever reason, we've got these soldiers that are standing in the parking lot like this, just ready to start marching. And then all of a sudden, somebody blows a whistle or whatever, and they start marching. So they're marching like this, in this direction. As people in the air in a helicopter are looking down, it looks like a wave front. It looks like the crest of a wave. Those people that are above notice that as these soldiers are marching, this guy on the end doesn't go quite as far in the same amount of time. Why? He can't go as fast. He's slowed down when he enters this new medium, the swamp. Can't travel as fast as he did on the pavement. Another couple seconds later, you got a couple of the guys, in fact, 3 of these guys in the water now. They're all slowed down. Wave looks like this. Another couple seconds, same deal. You got lots of them in the water now. And the waveform is going to look something like this. You'll notice that a few things changed. Number one, the speed of the wave changed. That's the biggest thing, the most important thing here, because that's what caused all this, right? When you went from a pavement to a swamp, you slowed down. The speed changes when the wave goes into a new medium. What changes because of that? Well, this would be wavelength. And I think you can pretty clearly see that wavelength decreases as speed decreases. So what else changes? The wavelength. What else changes? The direction of the wave changes, or theta. Put a little star by that, because if these soldiers happen to hit the boundary straight on, then the direction wouldn't change. But if they hit it at an angle, it does. V, lambda, and theta change. What doesn't change? As soon as the waves started entering the new medium, the part that didn't enter had 3 waves per unit time. The part that did enter still had 3 waves per unit time. What hasn't changed? The number of waves per unit time. In other words, the frequency doesn't change. V will always change, lambda will always change, theta will usually change if you go in at an angle, and F will never change. It always remains the same. Good? Let's talk about what happens when a wave encounters another wave now. You can see in the picture up here that I've got 2 waves. One wave, let's say, is traveling this way. The other wave is traveling this way. We'll call this one wave number 1. We'll call this one wave number 2. It doesn't really matter, though, which way they're going. What matters is that at this specific moment in time, this is what the wave's positions are. Regardless of which way they're going, the pattern that we're going to see as a result of these 2 waves encountering each other is going to look exactly the same at this moment in time, as long as the positions of the waves are exactly as they are right now. Here's what I want you to do on the template that I handed out to you a few minutes ago. I want you to look, first of all, at the portion of the wave or the portion of the waves that overlap. So in other words, I want you to look at here through here. The other portions of the waves, don't worry about that right now. Now what I want you to do is go on each vertical line from the graph paper, and I want you to do a little bit of addition. I want you to add the number of blocks above or below this solid heavy line that wave 1 is, to however many blocks above or below the solid line that wave 2 is. So in other words, if we look at this first vertical line right here, that we have some overlap, we can see that my first wave is about 2 blocks above, and the second wave is about 1 block above. 2 plus 1 is 3. So what we end up seeing at that spot, at that moment in time, is a wave that's neither 1 above or 2 above, but rather it's 3 above. Let's do the same thing with the next one. Wave 1 appears to be about 2 blocks above. Wave 2 is 2 blocks above. Add them together, it gives me 4 blocks above. Next one. Wave 1 is 2 blocks above, 2.5 blocks above. Add them up, 4.5 blocks above. Next one. Just about 2, just about 3. Okay, we're going to get just about 5. We don't have to be perfect on this, by the way. If it's almost 2 and almost 3, I don't want you to say it's 7. But 5 or almost 5 works. Next one, it's about 1.5, about 3. Adds up to give me about 4.5. About 1.5 and 3 and a bit. Just over 4.5. This is just over 1, just over 3, gives me just over 4. About 1/2 above, about 3 above. Going to give me almost 4. Now I want you to look at the portion of the wave, this portion of the waves that don't overlap. There's nothing to interfere here, it's just the one wave. So these X's are easy. Same deal over here. These waves don't overlap. Easy. Now I want you to do a little kindergarten work and connect some dots. So the wave that you see at that moment in time is actually a bigger crest than you had before. You had two crests. We get one single bigger crest. We call that constructive interference. If we had two troughs, we'd find the same thing. 1/10 of a second later, these crests are in different positions. We'd get a different pattern. It would still be constructive interference because it's still two crests, but it may be more pronounced if the waves are overlapping even more, or it may be less pronounced if the waves are overlapping a little bit less. But at that moment, at that one moment in time, this would be exactly what we would see if we took a snapshot of that. Constructive interference. Now what I'd like to do is take a look at the second diagram you have in your template, where we have a crest and a trough. Which way are they going? It doesn't really matter which way they're going. Okay, at this moment in time, these are the positions. I want you to look at the overlapping portion, which is from here to here, and I want you to add them up again, but pay attention to this. If you've got something below the x-axis, make it a negative. So here we've got 2 above and 1 below. 2 plus -1 is 1. 2 above, 2 below, add them up. 2 and -2 is 0. 2 above, 2.5 below. 2 plus -2.5 gives me -0.5. Okay, 0.5 below. I want you guys to finish these up here, please. Okay, finish these ones up right here where they overlap. Keep in mind that these ones aren't going to interfere. They're easy. Same deal with these ones. It's only this portion in here where they're interfering. Finish those ones up. And then, once you've done that, connect the dots. When you've connected the dots, you're going to find that you formed a wave that's smaller, which means we have not constructive interference, but destructive interference. This is what we were talking about. We were talking about when we did the slinky demonstration where the wave canceled out, or at least partially canceled out. This is what we're talking about with the noise canceling headphones, or Aiden's question about potentially canceling out an earthquake.